Recording is rolling. So, yeah, welcome to Thursday. Getting near the end of this week. Remind you guys that your projectile homework is due tomorrow. And remember what I did for that was, okay, I don't think I'm going to do this in the future. This seemed like a good idea at the time, but in retrospect, I think it was a bad idea. I gave you guys these couple of pages. There's chapter 3, problems from your book. All these problems are good problems. Right? These are my favorite problems. All the solutions are also available on Classroom. And then you guys got this page with the boxes on it, a bunch of projectile questions. What I told you guys was just to pick 8 problems. So it could be like 4 and 4 or like 2 and 6. Right? There are 6 scenarios on this page. And just write those up and turn those in for credit. So I think what I'll do in the future is pick specific problems. I think that'll make it easier for everybody. But just for now, this is what we got. So you guys stick to that. Some of you guys have turned this in already. So that is awesome. Right. Oh, quiz. I have a quiz for you guys. So it's clipped on the front of your desk. So the front of your desk. Right. Not the side that one's honors, but on the front. On the front. And it says AP on it. Right. You guys see that? Right. So this is take home quiz, open notes, just show your work and attach your work and turn it in by Monday. I guess if you want to knock it out tonight and not have to worry about it over the weekend, you could. But if you want to take a few days, check your work and make sure you got everything right, then turn that in Monday. Yeah. Any questions so far? I wanted to give you guys an update on Songwriting Club because I know I asked you guys last week if anybody would be interested. There actually was a lot of student interest, so I went and filed a paper for that. I thought I'd get a response by now. Hadn't heard anything. So also a bunch of students told me different days that they could join. So some said Wednesday. Anyway, we're going to do both of these days just because there are a lot of students who could do like one day but not another day. So we'll try this out and see how it goes. If you're curious, if you want to join, this will be after school, and these will be the first 2 meeting days. Have you guys writing songs, and it will be a fun time. So for today, I want to cover as much as I can from college physics. I think we'll get up to about here or so. Anyway, we'll do as many as we can from those chapter 3 problems, which are all 2-dimensional. So there's some projectiles. There's some that look like this, just 2 dimensions, got vectors going on. Actually, this one right here basically is number 8. So this is your starter question, except I made up my own numbers. But besides that, let's say there's like a box. It's being pulled by 2 ropes that have some tension in them. Okay? And the question is, what is the resultant of those 2 tension forces? That's say the magnitude and the direction. Now, maybe this box has some other forces on it. I don't know. Maybe it has a weight. Maybe there's a friction. We're going to ignore all that and just focus on the 2 tensions. It's like, what is the net effect of the box feels like it's being pulled due to those 2 ropes? Okay? So I've got 33 newtons straight up, and I've got 25 newtons being pulled at a 36.9 degree angle. How many of you guys are looking at that 36.9 degree angle saying, I know this is about to lead to a what scenario? That corresponds to a 3, 4, 5 right triangle, doesn't it? Which maybe gives you a hint that maybe this is going to involve like breaking this vector into components and working from there. So as usual, see if you can stay a step or 2 ahead of me. If you can stay a step or 2 ahead of me the whole way and beat me to the answer, then you should feel confident that you know how to do this. Okay. While you guys are getting a head start, let me recontextualize this problem. So there's a couple ways you can solve this. I'm going to solve it mathematically using vectors, vector components, I should say. But you guys remember graphically, you could use something called a tip-to-tail method, right? Where, say you can take this vector and slide it tip-to-tail with this guy, go pop it in place, or take this one and slide it up. And either way, isn't the resultant going to be something that goes like this? Right? And what that means is that this box feels as if there's one single force, net force, pulling it really hard, kind of in this direction. Let's get this going. Slide this here. You guys can still see that. See my numbers. Okay. Gonna redraw this. Just blow it up a lot bigger. You're gonna do some math, get some numbers. So, okay, got box, center of gravity. Okay. Well, on my picture, I'm just gonna start by drawing this 25 Newton force. This is how I'm doing in my notes. Right? At this 36.9 degree angle, which is about like that. Okay? So it says 25 newtons at 36.9 degrees from the horizontal. Okay? So that's just that one. Did you guys already break this into components? You guys are staying a step ahead of me. Right? So I'm going to say that pulling up and to the right. Well, it's kind of pulling up, kind of to the right. How much? Hey, I can quantify that because I know sine and cosine. I know some trigonometry. So I know that this like here will be 25 newtons times what? Sine or cosine of 36 degrees. Sine, because see how the side is opposite of the about 37 degrees, I should say. 36.9 degrees. Let's see what that comes out to. What is 25 newtons times sine of 36.9 degrees? Oh, it's pretty much exactly 15 newtons. Hold on to that number. Okay. What about this leg? Should this be 25 newtons times cosine of 36.9 degrees? And in this calculator, one reason I love this model, just scroll up, scroll over, cosine, and oh, it's pretty much exactly 20 newtons. Okay. But you guys knew that was going to happen because you guys told me ahead of time this is a 3, 4, 5 right triangle. And look at those three sides, 15, 20, 25. Doesn't that reduce to a 3, 4, 5 ratio? Sure does, doesn't it? And you guys knew that was going to happen. You guys told me it was going to happen. Okay. So great, we've got this guy broken into components that align with this Cartesian system. But remember that there was also this 33 Newton vector pulling straight up? Right. Now here's how I'm going to draw this in my notes. I'm going to connect it tip to tail. Slide right there, tip to tail. Go 33 newtons straight this way. 33 newtons. Okay. Okay. I could have connected them tip to tail the other direction. I could have gone up first and then up and to the right, and that would make like a parallelogram shape. It's going to end up in the same place either way. Okay. I can see that there's going to be a resultant that goes from the tail of the first one to the tip of the last one. I see this resultant because I connected these guys tip to tail. That's a tip to tail connection. Right? And this would become the resultant. Okay? And well, we need to figure out how many newtons that is because that would be the magnitude that's being pulled with. We also need to figure out what direction it is. So that's what we're working towards. Okay. All right, now remember that looks like overall this block is being pulled 20 newtons to the right, and it's being pulled 15 newtons up, but also an additional 33 newtons up. So how many newtons total is it being pulled straight up?
48.
48, because you guys did 33 plus 15. Yeah, got 48 newtons. Okay, so actually I care about this number more than either. So those two just made that. That went there, there. Okay. So I got 48 newtons up. I've got 20 newtons to the right. Okay. You guys good so far? Okay. What I want to do next actually is start fresh on a fresh piece of paper. Okay. So got that so far? Okay. Because otherwise I just got a lot of ink, but I've got a little bit more to write. Okay. So you guys see this big old triangle here? This big old triangle? I'm just going to draw that triangle. Here we go. Get these out of the way. So, a big old triangle made out of a couple components. I remember that it was 20 newtons to the right. It was 48 newtons up because remember that came from 33 plus 15. Right? All right. Resultant equals. How are you guys going to get the magnitude of that resultant? Pythagorean theorem. So, well, maybe we should write this out here. Okay. Resultant equals square root of 20 squared plus 48 squared. That many newtons. I'll factor out the unit, which is newtons. Okay. See what that is. So it's the square root of 20 squared plus 48 squared. 52? It's 52.00000. Hey, do you guys think that I gave you another special right triangle as the answer? Who sees it? That's a what triangle?
13, 12, 5.
Yeah! That's a 5, 12, 13. There you got it. You guys, 5, 12, 13? If you divide everything by 4, it comes out to 5 to 12 to 13. It's one of your special traumas. Yeah, so now you know. 5, 12, 13. It's a thing. Can you guys figure out, we still got to figure out what direction the block is being pulled. What direction? So what's one way to get that angle of theta?
Inverse tan.
Yep.
Inverse anything.
Inverse.
True. You could pick, you could be any of the trig functions inverse. If I pick inverse tan, it's what over what?
48 over 20.
Yeah. There you go. Opposite over adjacent, which is 48 over 20. The Newtons cancel. And what is inverse? Hey, what is inverse tan of 48 on 20?
That's 67.4.
There you go. 67.4 degrees. Yeah, you can say about 67 degrees. Oh, and then I have to specify that's, well,
Northeast.
yeah, something like that. Like, I'll say above the horizontal.
So if we were answering this, like our final answer,
Mhm.
how would we write it all? Is the final answer the angle, or do you want to say like it's going 52 newtons northeast at a 67.4 degree angle?
Yeah. So remember that vectors have two parts to them. There's magnitude and also direction.
Okay.
All right. So the magnitude is 52 newtons, and the direction is 67 degrees above the horizontal. Okay. Like that. Something here. Okay. Any questions so far? You guys all right with that? All right, so remember where that started. That started from these two guys pulling like that. Okay. Then we did something like this, then put it all together, something like that. Okay. Next one I want to do with you guys is number 12 from, oh yeah, number 12 from your questions. So it says a figure skater glides here, around a circular path. Now this one I need, where's my, oh man, I had a really good circle up here. Didn't they see a roll of masking tape? Oh, thank you. That's exactly what I need.
Just kidding, I'm passing it around.
It says, what number were we doing? 12, 12, number 12. Okay. It says you got a figure skater gliding around a circular path of some radius. Now, I'm gonna come up with my own radius, but you guys can follow along and get the idea, right? I'm gonna make a radius of, say 8 meters, which is different from your, but you get it. If she coasts around 1/2 of the circle, find a bunch of things. What's the magnitude of the displacement? Oh man, I'm so sorry. I want my notes to look really good, and I put that circle in the wrong place on the paper. I bet it's spinning up right too. All right, so that's what we got. It says she coasts 1/2 way around the circle. So let's say that she starts here on the star, and she goes around the circle to this point right here. Okay. So from here to here, point A to point B, call it point A, point B. Okay. So from point A to point B, okay, what is her displacement? From the star to star, it's how many meters? 16. Yeah, 16 meters. Okay. Remember, displacement, you don't care about the path that's traveled. Sometimes displacement or any vector is called path independent. So it doesn't matter the actual path. What matters is beginning point, ending point, straight line. Now the next question says, what is the distance that she skated? So distance that you skated. Now that actually would be like adding up this entire path, wouldn't it? Kind of like if you were in a car and the odometer on your car is adding up some number of miles, the same idea. So wouldn't that just be half of the circumference? Half circumference, which is half of, 2 pi r. Well, half of, looks like the 1/2 and the 2 cancel. Yeah, it would just be pi r. So that's pi times, and then the radius was 8 meters. So whatever pi times 8 is, 25.1 meters. Yeah, I can believe that. That's about right. Meters. All right, thanks. Then, says what is the magnitude of displacement if she skates all the way around the circle? So you start at point A, and you go back to point A. So the first question of displacement was point A to point B. Okay. So part C is just saying, what's the displacement from point A all the way around the circle back to point A? And what's the answer? 0 meters. So this is one of those sort of like definition kind of definition type questions. What is distance? What is displacement? Sometimes people throw a question at you guys like this. They might couch it something like, what was our average speed and what was our average velocity? So average speed, what you do say, oh, well, it's kind of like speedometer in a car. You could do the total distance over total time, right? And then that would be some number. But what is her average velocity from, let's say, point A back to point A? It would also be 0, but it would be meters per second, wouldn't it? It doesn't matter how much time it takes to get from A back to A. It might take her like, I don't know, 10 seconds, 10 minutes. Doesn't matter. If she starts and ends at the same point, then her displacement is 0 meters and her velocity is 0 meters per second. Okay. All right, next. Number 15. 15 says a vector has an x component of so many units and a y component of so many units. Find the magnitude and direction of the vector. Okay. Actually, this one's too easy for you guys, but let's just do it real fast anyway. Okay, so we got this vector, and it said so many units in the x direction. They give you a negative. I'm going to make it my own number. Let's say negative 35. Let's say meters. And a y value of, let's say 50 meters. Like that. Can you find the magnitude and direction? Figure that out. Hello, Mr. Griffin. Yeah, I'll send her. Hey, Caitlin, send for checkout. We send you to attendance. Attendance. All right, I got you checked out for attendance. So, go. Okay. Did you guys figure out what the magnitude of this is? What do you guys get? Here. I'll just do this on the calculator. Square root of 35 squared plus 50 squared. Did you guys get 61.0 meters? Like that? And what angle did you guys get? Oh, it's alpha. Do you guys solve for alpha? Did you guys do inverse tan of 50 over 35? So this would be 55 degrees. Say above the horizontal, like that. You guys got that, right?
Would it be negative 35, 50 over negative 30?
Yeah, if you want to play around with negatives, here. I wonder what would happen. I think it just comes out to negative. Yeah, it just comes out negative. Trying to think how you would interpret that. Yeah, Eddie?
Yeah, how would we interpret?
Oh, okay. See. Here, 35. Have to think about that. I think that I have to think about that one.
I mean,
Sorry, guys, but
it's the same-
it makes sense on the picture there, right?
It's the same answer.
Yeah.
If you put in a negative, it's the same number, it's just negative.
Yeah, alright, so.
Yeah, but that's not.
I'm sure there's a good explanation for that, but I don't have it in my head right now, so. So quick reminder, remember, you can take a trig function, either sine, cosine, tangent of some angle, and it will spit you out a ratio. You can take an inverse trig of some ratio, and it will spit you out the angle. Okay. That's what we just did. We did inverse tan, and tangent involves the two legs, so did that, and then that's how you get angles. All right, you guys can do that. Number 20, the helicopter view in this picture. Hey, look who it is. It's the donkey. Shows two people pulling a stubborn real. Yo, don't call me a donkey. Well, I'm gonna call you a donkey, so yes. But even though he's stubborn, find the single force that is equivalent to these two forces. Let's start with that one. So a guy pulling forward a little bit to the left, and a guy pulling forward a little bit to the right. Guess that? I think you guys have seen this before. So again, see if you can stay a step ahead of me. I mean, today's largely a review day. You guys have seen a lot of these concepts as we're going along. Gotta zoom out. Ooh, it's apparently raining marbles now. Global warming has reached infinite catastrophe. Vaporize all the glass. And so we got donkey, and a couple of guys pulling him. Now I'm going to make up my own numbers that are a little bit different from your book numbers. That way you can have a couple of different problems to compare to. But it'll be kind of similar. So say I got one guy pulling with 200 newtons of force exactly. And this angle is 75 degrees. And the other guy's pulling with, let's say 220 newtons of force. And this is a 60-degree angle. And so that's a setup. Right? Now, just like the box you guys saw a few minutes ago for your starter question, you guys know that there's some net effect of those two pulling forces. There's some net force. Figure out what that is. We're doing on. I think we're doing pretty good job. Okay, so what is the net effect? Right. Now, graphically, remember I could connect these tip to tail? Go. And then it looks like it's going to be kind of about here. Hey, can you guys look at what I've drawn and tell me? Obviously, the donkey is being pulled forward. But is that donkey being pulled overall a little bit to the left or a little bit to the right with my numbers? A little bit to the right. And there's actually two facts that both confirm that. This guy on the right is pulling a little bit harder, so that would influence it more to the right. But also, look at this angle. The fact that this angle is aimed more horizontally. See, if I call this angle like 85 degrees, then it might be a little bit ambiguous. Like, I don't know. Could be either way. But both those facts put together, yeah, definitely a little bit more to the right. All right, let's call this the y-axis and the x-axis. These guys are trying to pull them along the y-axis, but obviously they're missing a little bit. But that's okay. We'll figure out exactly how much by what is the net effect. So did you guys already beat me to the step of breaking that into components? Okay. So hopefully I'm just catching up to what you guys already have in your notes. That I'm going to take each of these vectors and break them into x and y components. Oh, look at those nice bright triangles. You guys have rulers on your desk so you can draw nice bright triangles just like me. And this side, you guys tell me what this is, and then I'll fill in the rest. This is equal to what times what? Yeah, 200 newtons times cosine of 75 degrees. This is 200 newtons times cosine 75 degrees. So I make this leg 220 newtons times cosine of 60 degrees. Okay. Then 220 newtons times sine 60 degrees, and 200 newtons times sine 75 degrees. Okay? That's all. I taught you guys how to do that even before I taught you any kinematic motion. Okay, so that's, yeah, you guys know how to do that a while. So I'll pull up my calculator. Let's get some numbers. Let's see, what is 200 sine 75? That is 193.2 newtons this way. Circle that, would be an important number. Let's see, what's 200 cosine 75 degrees is 51.8 newtons. Hold on to that number. What's 220 cosine 60 degrees? This is 110 newtons exactly. Hold on to that number. And 220 sine 60 is 190.5 newtons. Ooh. Oh, if we have a shelter in place, you guys might be locked in here doing physics for hours.
I need food.
We do all the problems. I will give you no homework. It'll all be done. All right. So, I see the stock is being pulled forward and forward. Aren't these two going to add together forward? But hey, what about the right and left? Are these adding together or are they subtracting from each other? They are subtracting. What you could do, you could swap in negative signs ahead of time, call this negative, negative if you want to. That might be helpful. Either way. I guess if you wanted to like program an equation that could like go into like some computer, you'd have to consider that. All right, so let's do that. Let's figure out what is the net force in the y direction. That'd just be these two guys added together because they're both pulling forward. So that's 193.2 newtons plus 190.5 newtons. There's 193.2 plus 190.5. That's 383.7 newtons forward. Okay. Hold on to that. Okay. But bunch of little steps. Nothing crazy in each step. This is stuff that we've done over and over and over in this class, but there's a bunch of steps. What's the net force in the x direction? Okay. Now here's where you guys said to subtract. It's got 110 to the right and 51.8 to the left. So that's going to be 110 newtons minus 51.8 newtons. So 110 minus 51.8. No. 1.8. It looks like 58.2 newtons. Okay. You guys beat me to all these numbers, right? You guys getting the same numbers?
Yeah.
Okay. All right. So now we know how much forward the donkey's being pulled, how much to the right overall the donkey's being pulled. You think we can just put this back together in the end? And that's okay. I'm gonna start this on a new page, I think, just to put the notes in. Okay. You guys good so far? Okay. All right, so let's go back, look at this donkey again, get a sketch of a smaller picture, what we started with. Okay. So donkey, floppy ears, tail, got being pulled this way, but also sort of this way. Okay. And remember I told you before we started doing any math that we could add these together tip to tail. So I could take this one, slide it, pop it in right there. Okay. Or I could go the other way, take this one, slide it right there, slide that way. You can see that parallelogram. So either way you do it, it'll work. You guys see this resultant right here? This resultant? That's really what we're solving for, the resultant. Okay? And, you know what? Sorry, I gotta start fresh again. Okay. So just blow that up real big. That's what I was trying to do. Okay. So we're just going to focus on that resultant that I just did. Okay. So this dark red resultant that I just drew, I'm just going to draw that right here. Okay. Where you guys know that this is 58 newtons to the right. So 58.2 newtons to the right, and 383.7 newtons up. 383.7 newtons. Okay. Okay. So we're putting this all back together, right? Yeah. So this is the net force. And how do you get the net force? The magnitude? Use the Pythagorean theorem. So it's the square root of a squared plus b squared. 58.2 newtons b(n) squared plus 383.7 newtons b(n) squared. All right, we got square root 58.2 squared plus 383.7 squared. That comes out to 388.1 newtons. Well, about 388 newtons. Maybe I was saying extra digits of those middle steps, but save rounding for the end. So that's the net force of the donkey feels. See if that sort of makes sense. He's pulled almost 200 newtons, or well, 200 newtons that way, 220 newtons that way. They kind of add together one direction, but they kind of cancel out another direction. The net effect is just a little bit short of 400 newtons. That definitely looks believable. So yeah, pass that check. And then furthermore, let's say you want to know, let's say this angle right here. Let's call this alpha and that beta, alpha and beta. Right? Isn't alpha going to be a little skinny angle and beta is going to be like a big angle? So set up one of these, alpha. Maybe I'll do inverse tan of, right. See if you guys can get this right. For alpha, it would be what divided by what? This would be 58 over 383. 58 over 383. Okay. So what's inverse tan of that? That is 8.6 degrees. I'll say right of forward. Well, that's alpha. How could you get beta? You could either do inverse tan of and then flip this fraction upside down, or you could just take 90 degrees and subtract alpha. So that'd be 81.4 degrees forward of right. So now we have a magnitude and also a direction for that resultant vector. Okay, guys good? All right, so like I said, that was a bunch of little parts, but there was actually there was a real good review question, right? So flash these in front of the camera one more time.
Good afternoon, faculty and students. We are currently in a shelter-in-place due to the weather. This means that everyone remains in their classroom with the door locked and no students or staff can proceed outside. Students or staff, if you are outside, please return to the closest classroom or come to the inside of the cafeteria. Once again, we are in a shelter-in-place due to the weather outside. Thank you.
All right. Oh, what just happened here? I like your back.
You can't.
All right, so one guy pulling forward to the left, one guy forward to the right. How much forward? How much to the left or right? Well, you get your sine and cosine components, and I circled those. All right, then next thing I did was, so let's add together the forward stuff. So I add this and this. And let's subtract the right and left stuff from each other because they're pulling opposite directions, right and left. Okay. So here's the forward directions added together. Here's the right and left stuff that's fighting each other on that axis. Okay. Then once we have those net values, then we could put it back together with the giant triangle. We say, well, here's the net effect to the right. Here's the net effect forward. In fact, it's really forward and only a tiny bit to the right. That's why alpha came out to be a really slim angle. And we got magnitude by doing Pythagorean theorem. Okay. That's the whole thing. Yes, good? All right, next one. All right. I circled number 23. I don't know why, because this one's too easy for you guys. So I'm going to do this really fast. You guys want to have a race? Number 23? Yeah, race time. Beat me to the answer. I'm going to make up my own number, so we all get to start at the same time. I don't even know what the number's going to be yet. I'm about to make them up. So it'll be the same scenario, though. So there's a cliff. We're going to take a rock. We're going to paint it like a baseball. We're going to throw this straight horizontally at let's say 20 meters per second. And the cliff height was also given. And that was, let's call it 100 meters. That sounds fun. 100 meters. Okay. Can you figure out, first of all, how much time does it take to reach the ground? Oh, I should draw a projectile path real fast. Right. How much time does it take to reach the ground? How far from the base I'll call it, maybe I'll call it D. Label this D. And parts, well, the third part, what's the crash speed? Actually, it says crash velocity, which involves two things, both speed and direction of the crash. So, well, I won't draw that in yet, but I'll come back to that. All right, so first part, the time. Now, I know that whether I throw this off to the side horizontally or drop it, doesn't it hit the ground at the same time? Which means that how much time it takes to fall has everything to do with the height of drop and nothing to do with the horizontal velocity. Right? You throw it twice as fast, still hit the ground at the same time. So I'm going to focus on that height, that drop of 100 meters. And I'm going to go to this equation, h equals 1/2 gt squared, which is a simplified version of v naught t plus half agt squared, but v naught y is just 0, so that goes away. Okay. Let's solve for t. Hey, since you guys are AP, I'll solve it in terms of variables. So 2h is equal to gt squared. T squared is equal to 2h on g. T is the square root of 2h on g. Okay. Now, the numbers I gave you guys, I set a height of 100 meters. And, well, it's implied that we're on Earth, so I'll use 10 meters per second squared for gravity. Square root of 2 by 100 on 10. Okay. Looking at 4.47 seconds. Okay. Hey, that's almost 5 seconds, isn't it? How far does anything fall in 5 seconds? About 125 meters. Wait, how'd you know that? What you guys even going to college? Come back here. Hey, look, that's a little bit short of, well, the 125 meters is a little bit more than 100 meters. So that definitely lines up, doesn't it? I can believe that. Next thing, what is this distance d? Where does it land? How many of you guys know the answer already? All right, what's the answer?
90.
Wait, yeah, 90?
Yeah, 90.
That sounds about right. Yeah, because I know that horizontally, it's just this. Right? Horizontally, there's no acceleration. Horizontally, you're just doing x equals vt. Right? And that's going to be, remember I told you that this guy threw it at 20 meters per second, horizontally? 20 meters per second. And it did that for 4.47 seconds. So multiply that. 20 times 4.47. Yeah. About 89 or 90 meters. There you go. So that's that one. Then the last question was, with what velocity does the stone land? Or baseball painted stone in my case. All right, so now this one, I bet most of you guys can get this, but think deeply on this because the next question that we're about to do, what we're about to tell you guys is going to come back. Okay. So see how I'm holding my roller flush to this projectile curve? It's like tangent to it, like flush to it. Okay. So that's the direction of motion. And right here at the bottom, maybe somebody at the bottom's like, hey, throw me that baseball. He's going to catch it. Do you think that it's going to land kind of at that sort of angle right there? See how that's like tangent to that curve? Right. Notice I did not draw it going straight to the. It's not like a line of sight. It's not how my pen is oriented. It's like that. Okay, guess that. Now that's some weird angle, but I could break that up into say, well, it's kind of coming across, and it's kind of falling down at the same time. Okay. Crossing down. Hey, you guys see a right triangle right there? See a right triangle? Right. And this would be how fast it's going horizontally. This would be how fast it's going vertically. Call it VFY. Okay. And you know what? You guys already know what one of those numbers is. Which one do you already know? VX. What is this? 20 meters per second. Because that's the same all the way through. Right? Same thing, right? It's not speeding up or slowing down horizontally. Gravity doesn't pull horizontal. It just keeps on. Now VFY, well, we got to do a little work to get that. So could I say, we got two options. I could play off the height of the cliff, or I could use the time, either one. Okay, so fast. if you play off the height of the cliff, you're using the third equation to solve for VF. If you use the time, you use the second one. I'll use the second one. I think it's a little easier. So final velocity in the y direction equals initial velocity in the y direction, which is just 0 because it wasn't moving up or down initially, right? Plus gt. So that'd be 10 meters per second squared times, is it 4.47 seconds, I think? So yeah, 4.47 seconds. Oh, I don't need a calculator for that. That's 44.7 meters per second, isn't it? Is it? Okay. Now that's strictly in the y direction. That's not its total speed. That's VFY. Okay. VFY. Right, so back to my diagram. I now know that this number is 44.7 meters per second. That's how fast it's going strictly down. Okay. Okay, so I know how fast across, I know how fast down. Oh, we are going in for the finish. Could you guys solve for the V total? Or maybe it's V crash, that's what I've been calling it. V crash by taking the square root of a squared plus b squared. So 20 squared plus 44.7 squared square root meters per second. Okay, good. It's showing up all right. Okay. So what is the square root? Hold on. Okay. What is the square root of 20 squared plus 44.7 squared? I'm looking at 49.0, I'll call it, meters per second. There you go. That's all three answers. So we're looking at the time was 4.47 seconds. The horizontal distance was 89.4 meters, and the crash speed came out to the crash speed is 49 meters per second. But crash velocity, there's one more thing we got to know, which is the angle that it's crashing. So I'll call this angle theta. Can you guys solve theta before I get it? So the angle of the crash, I got some scrap paper here. Okay. The angle of the crash is equal to inverse tan of dx over dfy. So dx over dfy. Again, notice that for that crash angle, notice what I did not do. I did not use the physical distances. I didn't do d and h.
Good afternoon, teachers and students. This is just a reminder, we are currently in the shelter in place due to the weather. We have turned off the bells until the weather clears, so please remain with your class and your students until we let you know that the shelter in place is lifted. Thank you so much.
Oh yeah, more physics. So notice that when I did inverse tan for the crash angle, remember that direction of motion is told by the velocity, right? Remember I told you that? Notice I'm putting in velocity values, and I'm making a big deal about this because I've seen many students in the past use D and H in this, but that's not what this is. That would be a line of sight angle, wouldn't it? Which is not the crash angle. You guys see that's two different angles? Okay. So that's inverse tan of 20 meters per second over 44.7 meters per second. See, what is inverse tan 20 over 44.7? Okay. That is 24 degrees from the vertical. Okay. Yeah, that looks about right. I can believe that, about 24 degrees from the vertical. So that's 24 degrees from the vertical. Okay. Just for comparison, let me go back and plug in what would the line of sight distance have been. If you go look at this guy, he's like looking at some binoculars straight at his friend up here, so like about to throw the ball at him. What would this angle be up to that corner? Wouldn't that be inverse tan of this distance of 89.4 meters divided by the drop height of 100 meters? Right? And before I hit enter, the reason I'm doing this is I want to do it for comparison. I want to compare it to this 24-degree crash angle. Guys, would the line of sight distance angle from the vertical have to be more than or less than 24 degrees? Has to be more than. This better be more than 24 degrees. And it is, it's closer to 42 degrees. Okay? You guys good? Okay. Again, that's something I see students do a lot. All right, we're gonna do one more, and then if you guys are held here for several hours, then you guys can work on that take-home quiz, get a head start on that. The last one I want to do with you guys today is, this is a classic problem right here. It's number 48. In a local diner, a customer takes an empty coffee cup to the counter for a refill. I guess there's number 48. So, got a counter. There's a floor. What's it say? The cup slides off the counter and strikes the floor at a distance D from the base of the counter. The height of the counter is H. Notice that this there are no numbers in this one. You guys see that? It's all in terms of variables. Find an expression for the time T it takes for the cup to fall to the floor in terms of H and G. Okay. And then there's some follow-up questions, but let's just let's get this down so far. So I got this coffee cup. It's sliding off the edge with some, call it B sub X, okay, the horizontal velocity. Okay. Gonna, and right there. When it does crash land, now this is several questions down the road, but just to get you guys ready, is it gonna crash on an angle that's flush to that projectile motion curve? Okay. I'll call this V crash. We're definitely not there yet, but we're eventually gonna work our way there. Something like that, right? What do we know? There's something to do with the height of the counter. There's something to do with the horizontal displacement. Okay. And something to do with gravity, which we're also going to treat as a variable. That way, we can, like hot planets, and we'll go to like some Star Wars planet and be like, here, have this coffee, rah! And then we'll figure out for a different gravity planet exactly how this will play out. Okay. Okay. You guys got that? Now, what exactly do we know or not know? We know the cup slides off the counter and strikes the floor at distance D. So distance D is known. Maybe we measure it. Let's say we know the gravity of the planet. This is known. Although it might not be Earth's. Let's just say we something we can plug in. Okay. Distance D. All right, and then the height of the counter is, hold on, no, I got something wrong. The cup slides off, distance D from the base. If the height of the counter is H, okay, so H is known, the height of the counter is known. Find an expression for time in terms of H and G. Oh, yeah, no, we're good. Okay. So those three variables, you know, that we don't know how fast somebody was sliding that. That's what we don't know. But they're not asking for that quite yet. The first thing we want to figure out is how much time does this take. Okay, but that's a good first step anyway. Right? Okay. Right. So we know the height of the counter. We know where it landed. We know the gravity of the planet we're on. You guys agree that there's some specific blast speed that would align with all this? In fact, you know what? Isn't this your guys' lab from yesterday? Well, some of you guys did this version.
Yes.
Right? Blast launcher. You had to figure out what was the speed of the launcher. Right? This is just that in terms of variables, isn't it? So let's figure out the time, and then we'll work out from there. Okay. So the time, shouldn't I be looking at vertical, like how long does it take to fall? Because if I give this a little tap and just it fell straight down, it's going to take the same time as if you threw it really fast horizontally. You crash, same time to reach the ground. So I'm just looking at the horizontal component. Now the full version goes y equals v naught y t plus half g t squared. Okay. But v naught y is just 0, so that goes away. And then, well, this y represents that height, that drop height. And then we got 1/2 gt squared. Okay. And notice that h and g could be known values, and you could solve for t based on that. Okay. So cross multiply the t, divide down the g. So 2h on g is equal to t squared. Then square root both sides to extract that t. So it's going to give me time is equal to the square root of 2h on g. Now, I could have any planet, It can have any counter height, and I can know how much time it's going to take to reach the ground. Notice it doesn't matter how far it went. Okay, so anyway, we got that. Next question was, with what speed does the mug leave the counter? Oh, that's that. That's what you saw for V sub x. What's that speed? Okay. Oh, do you guys agree we're going to be looking at horizontal information now because that's definitely horizontal speed? Okay. Didn't it go this far in this much time? It went this far in this much time. That's it. That's what we're going to do. So I'm going to say its speed is just distance over time, right? Is that true? Okay. I'll take this expression for the time and pop it in right there. So it's going to be v sub x, which is also the sliding speed of that coffee cup, is equal to however far it went, horizontal displacement, divided by square root of 2h on g. Okay. Now, I'll tell you what, if you wrote that on the AP exam, they would take that. They would say, yep, that's absolutely correct, got it. But I'm looking at fractions within fractions. I think we can make this look a little prettier. So I'm going to flip that bottom fraction and multiply it. I'm going to say this is the same thing as d multiplied by the square root of g on 2h. It's the same thing. In fact, if you guys look at the numbers from your lab, still grading your labs, I'm working on those, so it takes me a while, but get there. If you look at the numbers from your labs, they would align up with exactly this. If you want to figure out the blast speed, if you have this particular setup, pop, 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 that would solve it for you. Okay. Guys good? Okay. Now there's still last bit that we got to figure out, which is what is the speed and also direction of that crash velocity? So what is the crash velocity, which of course has two parts, speed and direction. Okay. So remember I wrote in v crash right here. I said we're going to come back to that. Well, now is the time. So that crash speed, well, it's kind of coming on an angle. Ooh. But the way we're going to approach that, it's the way we've been doing all these, and say, well, it's kind of going across, and it's kind of coming down. And if we can quantify those legs of this right triangle, then we can put it all back together. Right? Hey, isn't this just Vx?
Yeah.
And don't we already have an expression for that? That's this. That's this. Vx is this. It's this crazy combination. It's d times square root g on 2h. Right? We know that already. And this is v final in the y direction. Now what would that be? Well, let's go figure it out. So could I play off this? V final in the y direction is equal to v naught in the y direction plus gt, something like that. And v naught in the y direction is just what? How fast was this moving up or down, leaving the counter edge? 0. So this number's just 0, it goes away, ignore that, goodbye. V final in the y direction is, okay, so it's gravity, multiplied by, hey, time. Don't we have an expression for that? And it goes like this, square root 2h on g. I'm going to plug that, and right here, square root 2h on g. Okay, well, that's what that was. Is that right? Okay. That's good. And hey, oh, you know what? Look at that. There's a G here and there's a G here. They partially cancel out, but not exactly, right? Is that? Oh. Do you guys know what that simplifies down to?
I do.
Here, how about this? If you have, it is the square root of G. Yeah. In general, if you have like x divided by the square root of x, that's the same thing as the square root of x.
Good afternoon, teachers and students. It looks like there is a gap in the storm, so when the bell rings, we are going to transition to free lunchtime, and then we will lift the shelter in place until further notice. So when the bell rings, we will lift the shelter
Okay,
in place.
I could use like 2 more minutes, so here's what I'm gonna do. I'm gonna let the recording keep rolling. I'm gonna keep filming this, and then if you guys want to see the very tail end of this problem, then you can check it online. Okay?
Yeah, Pythagorean, right?
Yeah, it's gonna involve Pythagorean theorem and a couple other things. All right, so I'll see you guys Friday, and for the video, I'm gonna finish this out. So anyway, this ends up being square root 2gh, which you might have predicted because you guys have seen this before. This was the answer to the Galileo question. If Galileo drops a ball off a tower at some height, how fast does it crash land? You can see that right there. So I can go back in here and call this square root 2gh. Like that. Okay. All right, now we're getting real close to the end.
That was 2 years ago.
So to get the crash speed, v crash,
2 days ago.
I'll do Pythagorean theorem. So it's this squared d times root g on 2h squared plus this bit squared square 2gh squared, right? Because, well, maybe I should have preceded that with this. V crash squared is equal to b sub x squared plus the final y squared, something like that. Okay. So that leads to that. Pop in those pieces. Okay. So v crash squared is equal to, let's see, this would be, let's see, d squared times g on 2h plus 2gh. Right. Did you have a question?
No.
Oh, okay.
Very good.
All right. All right, so that was like that. All right. Now, maybe I could, well, I gotta take the square root of both sides. Right. So, I guess I could make this look prettier, but it would just be a square root of that, right? So v crash is the square root of all this stuff. All right, got d squared g on 2h plus 2gh. Right. Maybe you could factor out a g and get a common denominator and all that, right? But that'll work. Okay. That's a good expression I did. Right. Then what about this crash angle? This crash angle. Right. What's that going to be? Right. Well, I could do inverse tan. So this angle from the vertical is equal to inverse tan of Vx over Vfy. Vx over Vfy. Right? So that. Right. And that's going to be inverse tan of, say, Vx was this expression. So d times square root g on 2h. And Vfy is square root 2gh. See that? Okay. Now, if you follow the math real close, then what ends up happening is that this g and this g cancel. Right? These h's combine, and these square root 2's also combine. So when you clean this up, inverse tan, okay, so I've got this d, I've got, I've got a 2's that combine and the h's that combine that are also being square rooted, so the net effect is this, ends up being like this. And that is the angle theta. Now that's from the vertical. Exactly like I labeled it here. See this, here's the vertical, here's how many degrees from the vertical. So it looks like that. And notice that in this solution for the angle, what variable is not included there? Right? There's no gravity field. What that means, the fact that gravity cancels out, is that it doesn't matter how much gravity there was. If it was a really strong gravity field or a really weak gravity field, right? If everything else is the same, if the geometry is the same, let's say you're on Earth and you have a counter this high and you shove it off at some speed and it lands this distance away, right? That this crash angle is really based on the geometry. It doesn't matter how much Earth's gravity is. Maybe if you went to a planet that had more gravity, you'd have to flick it even faster so that it lands at the same distance. If you're on the moon, maybe it's a real slow speed. So this is dependent on the gravity field. Right? But this crash angle has everything to do with the geometry of this parabola, which does not include the actual gravity field.